Hey everybody, this is Marcus Brown with MLC CAD Systems, and today we're going to talk about flow simulation tips and tricks. This is kind of the second half of this topic. The previous webinar we did was on pre-processing. Now we're going to focus more on post-processing. So if you want to get caught up to the point where we're at right now, it's on YouTube ready to go, but hopefully these tips will help you with really any study you've got going on. So this is for advanced users. We're going to cover solving, specifically what you can do with the solver, understanding what's going on in the solver, talk about reviewing results and creating really compelling and informative visualizations so you can make sure the results make sense, so you can learn from the results. From there, you can refine the study. We're probably for this thermal study, we're going to learn quite a bit, and then we might even create a new study and study something new based on what we initially learned from our results. And then we'll talk about getting discrete measurements, reporting information, and sharing with stakeholders. So we got quite a bit to look at. Let's go ahead and jump right in. So this is our assembly. This is our study. We set this up in the last one. The basic setup is all of these slots on the side are open, which you see there, these capped, these are just lids. Those are all open to the air with static pressure. We have a 100 watt heat generation rate on this transformer, and we just want to see what happens thermally and make sure that we don't get any damage to these components because they overheat. So the first thing I want to do with this is just make some predictions. And the big thing about making predictions is understanding what it is that's important to you in the study, what things are you concerned about, and that's going to help you make decisions as you go finish setting this up. So my prediction is that because we're heating up this transformer, we're going to see the heat rise up, and this button right here, this reset breaker or whatever it is going to be the hottest thing in here. And then it's going to sort of continue up, and all these are going to be hot. And I'm thinking that this one might be a little bit, but really not bad. I'll bet you the air kind of comes up and just carries it up straight. This one's probably fine. These guys over here are probably completely cool. No problems at all with heat. I guess you could call that my assumption or my prediction, and we'll kind of see how close we are. So we're ready to solve, except we need one more thing to help the solver out. And that is to be able to give it some goals. So goals allow us to decide how exactly we decide when this is done. So for example, if you were trying to achieve a certain temperature of water, like say you're boiling water, you could visually go off of the actual effect of boiling. You could use a temperature gauge. You could do, a number of different things you could sort of pay attention to. And once that indication takes off, you say, okay, well, we've made it. But in this scenario, we're going to have fluid flow, and we're going to have thermal distribution, and we need to tell the solver which of those values are most important, so it knows not only when to keep going, but also when to stop, because we've achieved a converged solution. So these goals, first thing I usually do is create some kind of a global goal. This could be for, like a pipe system, like a valve. This might be mass flow rate. For this one, I'm not going to do mass flow rate. I want to know what the maximum velocity is, because we're going to have free convection here. Once it's fully developed, that will give us a maximum velocity. Oops, I selected bulk average there. And then I may also want to know, for example, the fluid temperature, sort of the maximum fluid temperature inside the domain. Right? Those two values give you a decent idea of, has the airflow sort of reached a converged value. I also want to do one a little more specific to the electrical components. So I'm going to create a volume goal for this transformer, and I'm going to say I want the temperature of the solid. Looks like we got to scroll down a little ways here to get the max temperature of the solid. And then we'll do one more volume goal, and I'm going to grab all these components because my concerns here is that these components are going to get heated up from that transformer, and they have a lower danger, threshold for temperature. I'll grab the circuit board as well. It's been simplified, but you get the idea. And again, we'll do the maximum temperature of the solid. each one of these is going to give us, some good insight and good information. Now, these global goals, those are pretty obvious, self-explanatory. Max temperature 1 and 2 in the solid, that's not the most descriptive, so I'll say max transformer temp, and then I'll say max component temp for all the other various components. So I feel really good about that. That's going to give us a nice efficient solve that we know is going to get fully converged. Let's run this. So we'll go up to Flow Simulation and hit run. We're not going to change any of these settings right now. You can do things like run this at another computer, send the study over, solve it, and then send it back. You can also turn off some of the cores so that you can continue to multitask while that's going on if you want to. But I think this is going to give us exactly what we need. Let's let this solver window come up and we'll talk a little bit about monitoring the results. I've had studies that have taken quite a bit of time to solve, and understanding whether or not you're running towards a massive problem really helps you save a lot of time. You don't want to run it for an hour or a day, or I've even had studies that lasted over a week to solve, and I was able to monitor their progress and make sure that everything was looking reasonable and realistic. So the first thing we look at, we've got this info page. This is usually where I focus first. It's going to tell you how many total cells. We've already optimized and reviewed this when we did the pre-processing webinar. But if it's 20 million cells and it's taken forever to do each iteration, you can kind of imagine it's just not going to solve in any reasonable amount of time. Now, another thing you'll notice is this is taking some time to prepare the model. I said this during the last webinar. I was being a little bit lazy. I suppressed a bunch of stuff, but I left a whole bunch of other stuff that really could have been removed to simplify things. That would have made it process faster, but I wasn't too worried about it because the mesh was going quickly. So you're going to see in different areas that this is going to require a little bit of additional effort to create the solver and to post-process some results. So just kind of learn from that and change the way you approach it if needed. As this starts to get going, we'll start to see the amount of time that the CPU has been running in the solver, and eventually it'll come up with a calculation for the time left based on how many iterations it thinks it's going to need. You're also going to see in here, let me pull this out a little bit wider. This is where you'll see some warnings. Now pay attention to the warnings, but this is probably one of the most common ones, and it's also one of the least troubling ones. A vortex crosses the pressure opening, and basically what they're trying to say is that a vortex is this circular rotation of air, and it's kind of self-sustaining. It feeds itself. If that vortex is completely inside the domain, then you understand the full effect of the vortex and how it's being developed. But if it's on the boundary, right, half the vortex is out of the domain, half the vortex is in the domain, then you may find that the vortex is actually not understood at all. And so the actual phenomenon, the actual developed flow will not be fully understood. That's what that's trying to tell you. For this scenario, we have slots, and all it means is that at some point on the face of that slot, air is going out, but somewhere else air is coming in. And it tells you the ratio, but for this one, I'm really not worried about it. We're going to let that continue. While it's solving, we can also look at things like the goals. It's nice to take a look at the goals just to see kind of what they're trending towards. If it's something super out of realm of possibility, that's an indication maybe you want to do something. We can also insert a preview plot, and the preview plot is really helpful. It does kind of slow down the solver a little bit to have these up, but it's really nice to be able to monitor what you got going on. I'm going to say I want to look at the temperature. I can make this a little bit bigger picture if I want, or I can crop it based on the area, turn on like the mesh overlay or something like that if I want, but this looks pretty good. I'm just going to click OK, and here is my plot. And so far so good. I mean, it's hot where it's supposed to be. It's cool where it's not. Feeling pretty good. Now, one of the things you'll notice is this thing is pretty much, showing right up where the plate hits the wall. I'm sorry, the components hit the back wall. So if you look, the front plane for this is actually right up back here. And so I'm going to edit the properties on this, and I'm going to change the offset of this front plane. And if there's a component that's right in the middle that has a plane you could use instead, you just go grab that plane. But the way I typically do it is I'll just rotate it so I can see it clearly, and then I will come in here and just adjust. And if you see that really thin outline of a plane over here, that shows me about where it's at. So you can just visually sort of say, yeah, that's about where I want it, right there in the middle of that volume of air. And now I'm getting a little bit more information. So again, so far it's looking really good. If you kind of keep an eye on the goals, as the goals start to converge, you're going to see the time of the calculation or the progress of the calculation typically jump way up. You can also see the goals converging or unconverging and having it go way down as far as progress. You never really know how long it's going to take until you measure that convergence value. In this case, these goals are going to speed this study up quite a bit compared to not using goals at all. All right, so the solution is done. We're ready to start taking a look at these results. Here are the methods, or the kind of the order of operations I do to create plots to start reviewing. Because the big thing you're looking for is a sanity check, and you're looking to learn from the results as much as you can. So the biggest and most common and kind of the most easy to do and informative is a cut plot. Right? I always do a cut plot. You can see it came in on the front plane, and I can kind of drag that forward to get it about where I want it to be. This is going to be a temperature plot, and I can actually hit the eyeball up here, the preview, and it'll kind of preview that plot as we go. Now, the geometry is kind of hard to see around, so maybe do like a hidden lines removed or hidden lines visible or something like that, or do a full wireframe, which is nice because then you can completely see through everything. You can also set the transparency up here in display, or just turn model geometry off completely. But this is going to work out pretty well. Next thing I want to look at is some of the options that I can apply to this cut plot. For example, I can come in here and say I want to put in some streamlines. And these streamlines, this is generated by the graphics card, meaning the lines are a certain distance apart, and as you zoom in, they'll actually just get closer and closer. So it's always maintaining a consistent spacing that makes it easy to look at. You may have some areas where you get a lot of overlap. We're going to talk about that when we get to flow trajectories, and that's typically just indicative of a vortex, a full vortex. You may also want to do a mesh overlay. This is a common one, just to make sure you don't have anything that's super mesh dependent. In other words, you don't want to have some weird shape that makes no sense that then you find out is because there's a massive mesh element somewhere and that's distorting your values. Here it looks like the biggest mesh elements we have are just dead center inside these big solid components, which is not a problem. We're not expecting that to be that interesting interior. But the fluid flow we refined pretty well already, so we're probably feeling good about that. And then anywhere you see a high gradient, just want to make sure you have enough data points there. So that looks good. I'm feeling pretty good about this whole plot, so I'm just going to click OK. And you could create one maybe on the right plane if you wanted to look at that, but we've got a pretty good understanding here. Let's do another one. Surface plots, I usually don't do surface plots unless I'm doing thermal, right? Thermal is perfect because it goes through and it just does the temperature of, for example, the solid or the fluid. Now, if I say use all faces, it's almost never going to give you a good result because it's always going to show you the inside of the boundary. So you never see what's actually inside there. So that works really well for external studies, not so much for internal, unless you do this one little trick, and that is to crop the region. And so this is the Z positive. And so if I bring that down just a little bit, and I click OK, what I've done is I've cropped the extents of that plot to make it a little easier to see. And you can even crop it on all sides and kind of break it down to just be those components, or you could select those components in the surface plot. Now, a couple things you're gonna notice here is that with these color charts, and we'll talk a little bit more about color charts in a second, these colors may or may not give you a whole lot of detail for what you're trying to accomplish. Because, for example, there's only 10 colors, you can see very clear lines, and that gives you some simplistic understanding of what's going on. If you want something more qualitative, you can come in and increase the number of colors a lot, and it really kind of gives you a different feel, a different perspective on things. So I recommend kind of doing a little bit of both, some high number of colors and some low. Another thing is the color scale. So this transformer is completely yellow to red, and we don't really understand the distribution very well on that one particular component. So if you want to effectively zoom in on an area, what you'll do is just come over here on the color chart and grab hold of either the bottom or the top and just drag it. So that one goes from red to yellow. I'm going to drag this up to yellow. And when I do that, it snaps back to the bottom, but it maintains that value. And when I click OK, I can now see much more detail about the distribution of colors or the distribution of temperatures on that particular one. The little block at the end of the thing, the end of the color chart indicates there is more information to be seen. And if you ever want to return back to where you were, you can reset to the global minimum or to the plot minimum. So if you're not seeing a very good or useful range of colors for what you're interested in, that's a good time for you to take a look at that color chart and adjust it if needed to give yourself an interesting thing. And you might even put in a surface plot for your hot areas and your surface plot for your cold areas, right? Or an overall. Just depends on what you're trying to communicate or what you're trying to investigate. Another very common one, I do this for pretty much all, that's a flow trajectory. And typically what I'll do is just come up here to my flow tab up on the command manager, and that splits my feature tree so that I can come up and grab things like boundary conditions. Now, here's the problem with that. I'm actually going to not do that one. That one does a decent job, but I want to just pick two lids just for fun. And I'm going to hit the preview button. And this is something I'll kind of show you what illustrates some problems people often get. They'll click the inlet or the outlet and they'll get this movement, and then they realize, hey, what's going on down here? It's completely empty. If you ever see an empty area, all that means is the bulk of the airflow that you picked does not end up down there. The bulk of the airflow does not go there, it goes somewhere else. Does that mean there's no air down there? Of course not. So what you've got to do is decide, okay, what do I really want? Do I want a really defined, specific understanding of those two lids, or do I want something more global and generic? So picking boundaries is typically a great way to start, or picking a component of interest is a great way to start. This is also another problem a lot of times I see, is you see these really thick areas. That's just that flow trajectory effectively just circling on itself over and over again, basically to infinity. And if you ever get something like that and you want to kind of clean that up for the visualization, come down to your constraints and just, reduce the length that it's allowed to go. And so now you see I reduced it down to 0.5 meter from 4. And now it does do the circles, but it doesn't do as many. And that keeps it a little bit more reasonable in terms of spacing. But probably your best bet, if you're interested in getting something really nice and evenly distributed in a view, just grab a plane or grab a value here that kind of puts it somewhere where it's meaningful. And this is really hard to see. Let's get this popped up a little bit higher. And then let's actually change the colors to be temperature colors. And let's put closer to 100. That's a much better value. If you go up to like 1,000, graphically, it's going to be difficult to see. And it's going to take a long time to solve. So here we go. Got all the colors. Actually, instead of spheres, let's do this one as arrows. Everyone's kind of got their own preferences. Depends on what you're trying to do. I feel like that's pretty good. But notice that the colors are predominantly blue to light green. So the only thing that's red is right on the surface of this guy. So let's do this. Let's just pop this down a little bit, and let's see if we can't get just a little bit more resolution. There we go. And the last thing I want to do is play. This is, cut plots are super easy to see very quickly what's going on. Flow trajectories are some of the most illustrative plots for understanding what's going on inside the domain. Because I can see in every direction and I can rotate it around, right? So I'm seeing recirculation in a couple different places. And this is something you saw over here in the cut plot. Let me show this so we can kind of look at them both at the same time. The 4 slots right over here, the 4 bottom ones, 3 and sort of the 4th one, they're all coming in with blue cold air. Right? Those are the intakes, which makes sense because it's getting heat. The hot air rises, that then goes out the top and draws in more from the bottom. And what you're seeing is these inputs, let's do this, let's hide that guy. These inlets are coming in and they're forcing most of the air to the center. And so what that ends up doing is creating, check this out, heat in this one component more so than the other. In fact, the component I thought would be the hottest is one of the coldest because it's basically got a fan, a dedicated fan blowing on it where that input or that inlet slot is. And if I come in here and kind of try to focus on these green components a little bit more, you'll see that the hottest component besides the transformer is actually this piece right here. And so, we're learning quite a bit. We're understanding a little bit more what's going on in the system. But the last thing you want to look at, in addition to understand where the airflow is and everything else, is just really pay attention to the values. So for example, I want to do a quick probe because I want to know how hot this transformer is. And as it turns out, it's 487. It's almost twice the boiling temperature of water. And that's almost always outside the operating range for electrical components in a cabinet. So this is a problem, right? These jets of cold air are coming in because this thing's practically on fire. So is this realistic? Well, yeah, it is for a pure steady state, but this is clearly not designed to be a steady state study or a steady state device. This device only turns on or off at certain duty cycles, or it's derated at times. And so we've got some more to do. We show you just a couple more quick ones. So a lot of times people create goals and think that if they don't create a goal, they won't have a way to measure something specific. But you can come down and create point parameters, surface parameters, or volume parameters and gather any information you'd like to know. So a surface parameter would be a perfect thing to put for basically a boundary condition. So if I came in here and I said, I want to know through these bottom 6 vents, right? These bottom 6 slots where I have my static pressure, I want to know the mass flow rate coming in, and I want to know the temperature of the fluid. Those are 2 things that are pretty helpful. I click show, and they're going to show up down here at the bottom. Local parameters are measurements you can make locally. Integral parameters are time dependent, so you'll see flow rate, volume flow rate, mass flow rate over here, and things like temperature. Looking at this, the minimum is 293, right? That's the ambient air coming in. The average is also 293. So we pretty much know this is all just cold air intake. The maximum temperature is 384, so there is some really hot air somewhere on one of these pieces. Probably there's a little localized circulation coming off of the transformer, but that's obviously not the bulk of the air. Average is averaged across the area. Bulk average is averaged across the volumetric flow rate or mass flow rate, depending on what you're looking at. So you can grab any individual measurement you want at any time. Volume parameter would be great to check, the average temperature of a solid component. One more that I'll do real quick is just an XY plot. So an XY plot is useful, especially for things that you have airflow through a channel or across various openings or something like that. Just create a sketch and then just use that sketch to define an XY plot. And for this one, I'm going to say velocity in the X direction, because that's going to be in and out. A couple things that I'll get from this. Let's see, show that. Oh, there we go. A couple of things I'm expecting to see here is I can see which ones are going in and which ones are coming out, right? I also see fully developed flow. If you see the fully developed flow is the velocity of the air across that, and that fully developed flow is different for each one because it's either coming in or it's going out. So kind of interesting stuff. Just a lot of really cool stuff that, in my opinion, helps you to gain insight into these types of applications. So you can look at these in the future and you can kind of tell what's going to happen based on what's going on. So let me hide all this stuff out of here and let's do something different. Let's talk about how we want to possibly refine this. So this is a steady state study that's clearly not going to get the job done for what we need. So what I want to do is turn it into a transient. And when you do this, if you're a beginner, I'd recommend creating a new study and setting it all up using the wizard, because it's going to give you a lot more help along the way. But I'm going to do this kind of manually because I want to be able to utilize what I've already developed without having to copy paste. Copy paste is great though, by the way, copy to project. But let's just clone this and let's just say internal free heat free convection transient. And this is just going to create a new study that we can then look at. So most everything here is going to be the same except a couple things. First I'll do is go to general settings and turn on time dependent. Now if this was a wizard, I would get time dependent, then I'd get total time step or total time and time step. But because we're after the fact, those are split now into two dialogues. So general settings, I turn on time dependent. And then the other one that's really important is calculation control options. And this is big because there's several tabs in here with different information that you need to know. First is the finished conditions. I talked about goals convergence. In a transient study, you can set up goals convergence and it'll stop once it's reached steady state. But I don't want to go that far. I don't want to stop when it converges on the goals. I'll leave them on for information only. But I don't want to do it that, and I don't want to do it by travels. So travels is sort of a measurement of how long it takes for a flow, event, like a wave, basically, to travel across your domain. And depending on the parameters you set, it can kind of determine how many travels it'll take. It's just a really slick way to calculate the estimated length for the solve of a study. But for this one, I want it to be physical time. I don't want it to stop till it's done. And let's do a 10 minutes, right? Let's do it 10 minutes, which is, 600 seconds? So that's the stopping condition. Don't stop till then. And then when it's saving is the other one we want to look at. It's always going to save the final result file, but I also want it to periodically save based on physical time. Right? Physical time makes much more sense to us than iterations or anything else. So we'll start saving results at 0 and we'll save them. Let's see, we did 600. Let's save them every 10 seconds. That'll give us 60 result files. I think that's a pretty reasonable thing to do. Now we're ready to roll with this new study. So let's run this. If at any point you ever need to stop a study, that's okay. You can always continue the study later. You just stop it anytime you want. You're never sort of locked into that. You could just, come back to it and finish it another day, basically. All right. So We've got our new study solver window. You'll notice that these are always going to be here because they're kind of the default values. But if you create additional types of plots, like cut plots and stuff like that, preview plots, those will show up. So this is going to start heating up, and we're going to start to see these values sort of converge where we want it to be. Now, a couple things I want to point out here to you. This is not the best place for it, but see how I can click this button up here called Refine? It's disabled for the transient, but it's available for steady state. That refine and the one found in calculation control options for refinement, those are the same thing. And effectively what it's doing is it's saying it does a solution adaptive refinement. If you see an area of high activity and low density of mesh, it will refine that area. And in this, think of it, the most common thing would be for like a hypersonic shock wave. If you were doing hypersonic, supersonic flow over, a nose cone or something like that, and you saw a shock cone form, the location of that shock cone is not known until you solve. Once you solve, then you can refine those areas very clearly, and it does a really nice job of taking care of that. So we're not going to need it here, but that's a really useful option. What is very useful here is some of these solving parameters. And we have things like stationary and solids, nested iterations. Hit the help button to really dig into what each one of those means. And I can modify other things, but the big one I want to do here is called flow freezing. Flow freezing says, hey, once the air gets developed, right? Once the flow really starts to get moving, I would like this airflow to not be calculated every single time. I want the airflow velocity and pressures and stuff like that to more or less freeze temporarily while things are heating up or slowing down. Now, I wouldn't want to turn that on at the very, very beginning because there's a lot of stuff changing very quickly. But as the velocity, right, as the velocity field inside my domain starts to sort of trend towards a single converged value, if I enable flow freezing, the solver will only solve for temperature. It's not going to solve for velocity every single time. And it'll run with sort of static airflow, right? The air's moving, but it's not changing how it moves. It'll run with static airflow and solve for the temperature as it goes. So really helpful if you have a long thermal study, transient study. Flow freezing is absolutely awesome. So taking a look at the time here, we've got calculation time left. Man, we're 50 minutes, and this whole webinar is less than an hour. We are at 17 seconds so far, and the current time step is about a quarter of a second. So let's go ahead, and we're just going to skip ahead a little bit. We're going to do the calculation control options, and we're going to turn on that flow freezing strategy. So say periodic flow freezing. I'll just leave the defaults. That should get us a good result. And you'll start to see all of a sudden now my time step is now from a quarter second up to 3 or even 6 seconds. And that's because of that flow freezing sort of turning on and off depending on what's going on. And as we get further along, you'll see that the current time step trends towards eventually being the saving time step. So if you tell it you want to save it every 10 seconds, your time step will never go above that, which is good. You don't want it to ever go too awful far up. But then again, you also don't want to save so much that you're going to have problems on your hard drive. Now, let's talk about a little bit about the hard drive and files on your hard drive. So this is the folder where these files are found. And I have, along with these other random folders that I've created for myself, I've got 2 subfolders here. Every study you create creates a new folder. It's named based on the order you create them. Number 1 is my steady state, and inside here is 1.fld. And in the second folder, you'll see a 2.fld. That's your result file. These other things are helpful and necessary for certain things, but the FLD is what you can post-process to get your plots and things like that. Now, if I was to come up to the second one, this is where we have a transient study. We have 2.FLD. That represents the latest and greatest value, but I'm also getting all these other R underscore, and then it's like 105, 106, 107. That is the iteration number of the solver, and it's saving them every 10 seconds. So we started out with 34 iterations to get to the first 10 seconds. Then it took 71, 73, 75. And you can kind of see it's variable from there, but it's saving a lot of data. So we're expecting to get about 60 result files. That's reasonable for this study because each result file is not terribly large. But just understand that the more you do, the more you save, the more hard drive space is going to get taken up, and the longer it's going to take to post-process in a lot of cases. All right. We're getting really close here to the finish, but I want to prove a point, if I hit stop, it'll say, do you want to save the results? I'm going to say yes, and it's going to allow me to post-process what I have. I can always come back and just run it again, and when I run it again, it'll say continue calculation. It'll finish as if I never stopped to begin with. So that's a really handy thing to do if you're like, hey, I feel good about where it's at. I want to learn what I can from the results. And if it turns out that's what I want for my final, then I'll just finish out the solve. And if not, that's okay. I can fix it and start over without waiting again. All right, so let's look at some results. Obviously, we still have our plots from before, the benefits of copying or cloning the study. And if we come into wireframe here, you start to see, that's pretty good. You see that this is 2.FLD. It's at 560 seconds. That's the final time that it saved. And it's behaving very different than what it was last time. And again, this kind of comes down to the amount of airflow and the speed of that airflow caused by the induced free convection. This is just not quite as extreme, and so it's going straight up and doing a lot more of what I kind of expected it to do. In fact, let's see how hot some of these components are. If I start to just continue dropping it down, you'll see we're really hitting hot air on these components right here. So that's going to tell us something. And we are still getting a decent amount here. That might be from conduction coming across. I'm not sure exactly. So, all right. So that's a lot of good information here. I do want to do one thing real quick, and that is to animate this cut plot through time, right? I want to see how it heats up through time, and I want to make an animation for it. Before I do that, I want to clean up everything a little bit. Right-click computational domain and hide, and that gets rid of that cube. Right-click at the very top and say hide global coordinate system, and that gets rid of that little coordinate system. Just kind of clean stuff up, and then I can further hide individual items if I wanted to make this a little easier to see. But I'm going to do an animation for my cut plot. Now, a cut plot animation, typically what happens is it will animate the position of the cut plot plane through the domain. But in this scenario, I don't want to go through the domain. I want to go through time in the time domain. So here's how you do that. You'll use the animation wizard. So I'll come in here and click that animation wizard. Tell how long do you want your video to be? It's just going to spread it out, whatever it is, to the one you want. Delete all existing tracks. Okay, that's the key here, one of the keys. So then we click next. We don't want to rotate it. But when we click next one more time, if it's a transient study, you'll get this option to do scenario. So scenario is through the time domain. It'll do a uniform distribution through physical time from the start to the last result file you have. I'll click finish, and there it goes. It creates each one of these keyframes. And each one of these keyframes corresponds to a specific time, result time, and a specific result file. This is file 136. But that represents pure linear time on the scale. The only other thing you need to do is choose which plots you want to be visible and at what times. So for example, let's say I want to do the cut plot through the whole time. So I'll right click at time 0, insert control point, and drag this out to the end. That is now going to be active, and the cut plot will be visible the entire time. I may then decide, hey, I want to do the flow trajectory near the end, but only near the end. I want to turn that on and kind of see what the developed airflow is once it kind of gets going. So when you're ready, hit play. Now, you may want to instead hit record, especially if these are really, really large result files. Hitting play, it's going to go so slow that you're just not going to be able to gain any insight. So I hit record, go grab coffee or something like that, come back, and then I can just play the video through, let it loop, but it's going very quickly, so it's easier to see. This one's going pretty quick. It's not too bad. And we can start to see the airflow, how it develops, where it's going, what's going on. I changed the color chart because I'm not overly concerned about the temperature right now of that transformer. But if I was, I could go in and add a probe or add a surface parameter, and that would display on the screen and would be picked up in the video. So, your result processing, a lot of times you're going to end up really using those in combinations to get what you're looking for. All right, so it's getting about to where 7 seconds, it's going to turn on that additional flow trajectory plot. If you ever wanted to do things like rotation or move things around or something like that, those would be keys here on the geometry line. And you can get a decent amount of really nice, animation capabilities here inside Flow. And so now we turn on and solve the flow trajectories. This is going to add some time to generating these images, obviously, but it does a good job. If you're doing something, and you really want a nice smooth animation, you are going to have to really decrease the solving time step so that you get a lot of data and you can generate something really nice and smooth. All right, for the sake of time, I'm going to go ahead and stop this because I would like to take a look at reporting. So here's our animation if we ever need to get back to it, but right above it is the report. Right click report and create. So here's how this works. It's going to create a document. And if you've created a brand new document, or if you have an old report and you're trying to fill more data into it, it's going to show you all Word documents that are open. So if I had a document open right now, it would list it here and it would say unattached, and you could attach to it and start feeding it. But I'm just going to create a new one from a template. And when you say from template, you're going to see these various standard templates. My flow report for MLC, that's very much like this flow simulation report. It's just kind of changed the formatting to fit some more of our company branding and colors. So here it is, and I'll bring this guy over here. And let me actually just kind of go side by side with this, because this way you can kind of see kind of the iterative process of how reports are generated. So in my report, I have some standard information here that I can fill in or modify. I've created some kind of reminders for myself. So I want to put a model picture on the front page. So let's just come over here and change this and hide this. And this image right here is where I want to put right in this report, right here. So what I'll do is just come to pictures and charts and say this image, I want to go to the current position in the document that I am attached to. And I'll say add to report, and it throws it in there. Now you may find that it goes really big. That's, a little bit of formatting here is going to take care of that. And you may want to, crop it and things like that. Let's do center, crop out the heads-up display at the top. But you get the idea. right? Very easy to add reports in from your model. So continuing on, I got my table of contents. This is all set up the way I like it. And what I've done is sort of pre-prompted the information I want people to type, how I want them to type it, summarize the goal, what questions were we trying to answer, what assumptions did we make. The rest of this is auto-populated based on your study. So you don't need to worry too much about any of this stuff. But here pretty soon you start to see things like boundary conditions. The boundary condition for the static pressure, it tells you everything you need to know, but it does not give you an image. So to do that, what you may want to do is sort of come out here and, create maybe an image that shows, right, what these are. So I can say, come in here and just go ahead and add this one right here. You will have to scroll back down because every time you insert it goes all the way to the top. But this kind of gives us the ability to really quickly add just a little bit of visual context, right? This is not required. This is totally up to you. But as you go through here and you are defining things, you probably want to add some visual supports. This is a big one right here, the results area. This is where I'll do like recommended plots. I'll say, let's do a cut plot. So come over here, create my cut plot, visualization, and add that to the report. And if you want, you could very quickly add a bunch of them to the end of the report and then move them where they need to be, save you a little bit of time moving around. But you guys get the idea. The report is pretty straightforward. Again, if you ever have created this and you need to go back and add more to it, just open it up, come in here, and click on the one that's open and hit attach, and it'll grab hold of it, and then you can start feeding data into it. Don't forget to save it. Right now it's just a temporary document. There's not saved anywhere, so save as you go, and you're going to have a great time. So I really hope that this was informative and useful for you. If you have questions about anything, go through the help file or take a look at these various reference guides that kind of give you more information about exactly what all those solver options and other things, exactly what they do and how they work. But at this point, I'm just going to open it up for questions. So if you're on the webinar right now, type those questions in. And here in a second, we'll do a live Q&A. If you're on YouTube watching this later, or if you are on the webinar and you want to go to YouTube later, join in the conversation in the comments. And please subscribe. I'd really appreciate if you could kind of support us and let us know that this is the type of stuff you enjoy. We are going to commit to continuing to create lots of great informational videos like this. So join us if you can, and let us know what we can do to help you out. So let's see what we got for questions. Thank you.